let's move on to question 1d. So it shows here that figure 3 shows two cells A and B and a galvanometer G, which is connected to slide wire OX. So OX is a wire that you allow a jockey to slide on it. So the jockey is Y and the jockey is sliding on this slide wire OX. Okay, OX is static. Y is the one that is moving, sliding along this OX wire. Okay, the length of the slide wire is 1 meter. So this from O to X over here will be 1 meter and its resistance is 40 ohm. Okay, so the resistance of this piece of slide wire over here is 40 ohm. Okay, when the distance of OY, which is from here to the jockey's position, is 40 cm, the galvanometer achieves equilibrium. So when we say galvanometer achieves equilibrium, that means that there is zero deflection in the galvanometer. It's not deflecting to the left, it's not deflecting to the right. And when we say galvanometer achieves equilibrium, what does it mean is that there is no current passing through the galvanometer. Okay, so now they say if the EMF of B cell is 2 volt, which is this cell over here, if it has an EMF of 2 volt, and they ask you to ignore the internal resistance, now calculate the EMF of cell A. Okay, there's a lot of information. Let's try to label everything that we know inside the diagram. Okay, so it says that the length of this slide wire is 1 meter, so we can probably label that. Okay, so this whole length of the slide wire is 1.0 meter, and the resistance of this slide wire is 40 ohm. So I can write resistance of the wire. So let's write OX. The whole length over here, the resistance is 40. Okay, then they say when the distance is 40 cm for O and Y, which is from here to here, okay, it's 40 cm, 0.40 meter. Then the galvanometer achieve equilibrium. So if the galvanometer achieve equilibrium, you should expect I equals to 0 on this path over here. I here will be 0, I here will be 0. So I across this whole thing here, from here to here will be 0. Because here, if there's no water flowing, then here should not be water flowing. You cannot have water flowing here, but no water flowing here. So if they tell you that there's no water flowing through here, then there will be no water flowing through here, 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 no water flowing through here. But here there can still be current flowing because here there's a junction. So you can have current flowing here, not entering here, but straight away turn into here. Because here you want to make sure the current is 0, because this is what happened when the galvanometer shows 0 deflection. Okay, so they say if the EMF of B cell is 2 volt, which means that here you can write equals to 2 volt, then now they ask you to find EMF A, which is this one over here. Okay, so the idea of a potentiometer, it allows you to determine EMF of an unknown source of EMF. Okay, usually the EMF that you're not sure about, it's usually the secondary EMF, not the primary EMF. But in this case, they try to flip around the situation. What if you know the EMF of the secondary power source, but you don't know the EMF of the primary power source? How do you find it? Okay, so for a potentiometer, right, for this kind of potentiometer, the main working principle is that you have to slide the jockey, which is this Y position here. You have to slide the jockey until the galvanometer shows 0 deflection. Okay, when the galvanometer shows 0 deflection, then the current will be equal to 0 across the galvanometer. So from there, you can infer that this whole journey that I highlight here, from this arrow to this point over here, we will have 0 current. But here you can still have current. I'm just saying this path over here should have 0 current. Okay, So when that is the case, right? Okay. The potential difference across this slide wire from here to here, the potential difference across this path over here will be equal to the potential difference across this path over here. Okay, I should use a different pen actually. Let me use another different pen. Okay, the potential difference across the yellow path will be equal to the potential difference across the green path actually. Okay, so why do we know that? It's because of Kirchhoff rule as well. Okay, Kirchhoff rule tells us that at any loop, the sum of V must be equal to 0, right? Okay, so if we take our starting position to be at, if you take our starting position to be at 0, not 0, at O, then we move through this direction over here. Okay, we move through this loop. So let's try to do Kirchhoff rule together. So it will be sum of V equals to 0 for this loop. So we know that the first thing that we will pass through is this slide wire OY over here. And we know that for this circuit over here, the current will be flowing from the positive terminal through to the negative terminal. Okay, this is the direction of flow of current over here. So you should expect that this journey over here, our highlighter is following the direction of current. So you should expect it's a negative IR. But this time the R is the resistance across the wire from O to Y only. Okay, you are only passing through from O to Y, you are not going over to X. So you only need to consider the resistance of the slide wire from O to Y. So this is the portion of the journey from here to here. Okay, then if you continue your journey using a highlight pen, you'll pass through a galvanometer, but you assume it's an ideal galvanometer, so it doesn't affect your circuit. So the next thing that you pass through will be epsilon B. Okay, you pass through epsilon B going from the negative terminal. Here is a negative. You're going from negative terminal to positive terminal. It's a potential gain. So it's a positive epsilon B. Okay, so if you continue your journey, then you get back to the point where you start. Okay, so now this will be equal to 0. So from here you can see that I R O Y is equals to epsilon B. Okay, they both have negative sign on left and right, but you can remove the negative sign. Okay, so what is this trying to tell you here? It's trying to tell you that this is the potential difference across from O to Y, and it's equals to the EMF of cell B. Okay, so the potential difference across these 2 points of the wire will be the same as the EMF of cell B. We already know EMF of cell B is 2 volt. We just need to determine VOY. So we know that VOY here will also be equal to 2 volt. And from there, we have to relate it to the EMF of cell A. Okay, so how do we determine voltage across OY over here? Well, that will require some understanding of potential divider. Okay, so let me redraw the circuit on the right in order to show you how does the potential divider works here. Okay, so here we have our first resistor, which is the 5 ohm resistor. Then going downwards, we have the slide wire. Okay, but instead of drawing this slide wire over here, we can represent the left-hand side of this slide wire, left-hand side of the jockey as one resistor. Okay, we can represent the left-hand side of the jockey as one resistor, which we call it as ROY, and we can represent the right-hand side of the jockey from Y to X as another resistor, which is RYX. Okay, then you should expect that ROY over here will have how much resistance? It will have length of OY divided by the length total times the resistance of OX. Why is it so? Because you learn from a very early subtopic that the greater the length of a conductor, the greater the resistance, right? So if you know the total length is 1 meter and you know that O to Y is only 40 cm, that means you are only taking up 40% of the total length of the slide wire. 40 divided by 100 cm means by you have only 40% of the length of the whole slide wire. And 40% of the length means by you're taking up 40% of the resistance actually. Because the longer the length, the greater the resistance. So you only take up 0.4 of the total length. So you only take up 0.4 of the total resistance of the wire. Okay, and of course, RYX over here will be length of YX divided by length total times ROX. Okay, so now you can see that this whole journey here, if we ignore what happens down there, because the current is equal to 0, so technically we can ignore the bottom part of the potentiometer. So I'm not going to draw it over here. If we ignore the bottom part and look at this upper part only, we can see that it's actually just a series circuit with 3 resistors, ROY, RYX, and R5 ohm over here. So if you want to find the potential difference across this slide wire from O to Y, what you're actually doing is you're finding the potential difference from here to here. This is what you are finding over here. And if we talk about it from the concept of potential divider, well, you are just splitting the cake. You are splitting the potential of epsilon A, splitting it to ROY, splitting it to RYX, and splitting it to the 5 ohm resistor. Okay, so in order to determine VOY, it can be equals to, you know that down there, if you use potential divider, you have to add up all the resistance in that path. And all the resistance in that path will be the resistance of the 5 ohm wire plus 5 ohm resistor plus the resistance of the whole wire, OX. Okay, so this is the wire. Okay, but what you're interested in is only the portion related from the journey of O to Y. So you're only interested with R or Y. And now what you put at the back is just the input voltage. The input voltage is epsilon A. The output voltage is VOY over here. So you put epsilon A over here. So this is how you construct the equation to determine the potential difference across point O and point Y. Okay, so now what you can do is you can either finish your calculation, finish your substitution over here, then bring it over, or you can just merge it now. Okay, so I'll merge it now. So what I'm going to do, I'm going to bring this right hand side here to replace the left hand side over here, and I'm going to write it here. That's the worst arrangement ever. Okay, so you know that this will be epsilon B equals to ROY R5 ohm plus ROX epsilon A. Okay, you know that ROX over here is 40 ohm, and you know that ROY over here can be determined through this relationship over here. So now everything can be substituted already. So epsilon B, which is given over here, it's 2 volt. ROY over here, it's 40 cm divided by 100 cm times the ROX, which is 40 ohm. Okay, so 0.4, 1.0, total resistance of the whole slide wire is 40 ohm. Divide by 5 ohm plus 40. Okay, Rx over here is 40 ohm once again. So you're left with epsilon A needed to be found. So epsilon A, if you calculate it, it will be equals to 5.625 volt. Okay, so that's how you solve this problem and how you obtain the EMF of this cell A over here. So one thing I would like to say is that it is important that you are able to find this relationship over here. Okay, because this relationship change depending on how the circuit is being installed. So let's say if this battery over here has internal resistance, then you have to consider the internal resistance when you are doing your sum of V equals 0 over here. So there might be a negative or a positive I internal resistance. Or if you have a path connected parallel to the battery, then it will be another issue as well. So it's a case-by-case thing, and there's no fixed formula or fixed equation that can help you to solve all equations. You are the one responsible to determine what is the equation over here. You can determine it using Kirchhoff rules, but if you want to use Kirchhoff rule, make sure you are able to determine where are the current flowing, where are the current not flowing. That is important. Okay, so you can determine this equation using Kirchhoff rule, but after that, what is the key after that is to manage to determine VOY over here. So you have to understand that the resistance depends on the length, and you have to use the concept of potential divider to solve the problem over here. So it's a question that combines many different concepts, and it requires you to be very firm, strong with all these little concepts in order to solve the problem of potentiometer. But again, it comes with practice, it comes with experience, and I believe through many different exercises, you should be able to see how to analyze this kind of question systematically. Okay, so that's all for question 1D, and that's all for Pre-LEPAK chapter 3. Thank you very much.